oil shale development? And of course, it depends. I suppose is the answer, as with most of the questions we've been asking today. But to help us sort of sort through some of these issues, we have one of the most prominent researchers on the subject of oil shale. He is Jerry Volk, of course. We've already heard insightful questions from him from some of the other speakers. He's the director of the Center for Oil Shale Technology and Research at the Colorado School of Mines and the chair of the annual Oil Shale Symposium, which draws people from all over the world to come and talk about issues about oil shale and oil shale development and technologies. I thought the most interesting thing in his resume, though, which is in your little outline, was that he personally removed 75 grams of plutonium out of the city of downtown Denver. And I'm not sure what it was doing there, but thank you, Jerry, for taking care of it. We're all grateful. Jerry Volk.
Thanks, it's a pleasure to be here. And now that it's gone and promptly disposed of it with, I can say that it was at the Auraria campus and it was used to teach students about neutrons. And it was weapons-grade plutonium. I want to start with, I think, three things, at least two opinions. The first is that it is my study conclusion, but not an objectively demonstrable fact, that the economic viability of oil shale will depend almost entirely, will be critically conditioned by value judgments made by the people of the United States as implemented by their representatives in Washington. That might scare you, it does me a little bit. The second thing is that Henry David Thoreau said that patriotism is the last refuge of the scoundrel, and I've concluded that in scientific and engineering discussions, that last refuge is thermodynamics. I studied thermodynamics 5 times, and I never heard anything said today that sounded conclusively related to what I learned in thermodynamics. So we have this chicken and egg problem. Our values may decide whether companies can actually make an economic go of this. I'm going to talk about
it's the down arrow.
Oh, down arrow. Oh, we have a fun slideshow.
Oh, is that what we're... Oh,
yeah, that's what I was looking for. I'm trying to remember. That's a PowerPoint. PowerPoint, I'm stuck.
Okay.
I forgot it was the PowerPoint that you put up. I thought I had the. This is PDF? Yeah.
Yeah. Sorry.
Anyway, it's the smaller file. So I'm going to talk about a few things. What is oil shale? Because we've heard a little bit about it. CO2 emissions from oil shale, because that's what I was asked to talk about. Some related issues to try and frame that CO2 question in a larger framework. And of course, I have to finish up with a little bit of comment about the center that I direct and the symposium that just got mentioned, which truly is the place if you actually want to know what's going on now about oil shale. That's where you have to be in October. I noticed when I looked down the list here that of the 17 speakers and moderators on this agenda, only 6 have attended the Oil Shale Symposium in the past 4 years. I could add one more if I allowed the surrogate who actually delivered the talk to be counted in that. But, and I think what I've seen is a very strong correlation in the technical basis of what's being said to attendance at that symposium, where 300 people from around the world talk about what's actually happening in oil shale today. So what's an oil shale? It's an organic rich mudstone, generally formed in a lacustrine, lake, or marine environment. Most of these are carbonate rich. Some of them are not classical clay-rich mudstones. They're rich in keratin, which is a complex mess of hairy organic chemicals left over from the partial breakdown of algae and bacterial remains. It's an immature precursor to oil and gas. A lot of complexity in talking about whether the stuff that's coming out of the Bakken now is shale oil or not, and that's all terminological. It doesn't actually have a whole lot of relevance to discussions about the viability or interest in oil shale. But oil shale, as we classically know it, produces oil on short-term heating to temperatures above about 300 degrees C. In other words, you do not have to wait for it to get buried several thousand meters down and generate oil on its own, which could take tens of thousands to hundreds of thousands or even millions of years. So, is it oil, is it shale? This is a bit of myth busting I'm going to do here, because this canard has been around for a very long time. It's still up there on Wikipedia. The idea that oil shale is a misnomer. Geologists wouldn't necessarily classify the rock as shale. Well, will they or won't they? It's an ambiguous question. And its origin differs from crude oil. Yeah, it's not liquid, it's solid. Same thing here, but why are they constantly asking about this? You know, what do we really care about the rock, as long as we can get a product out of it? I think the answer lies in this last quote. As geologist Walter Youngquist once wrote, bankers won't invest a dime in organic marlstone, the shale's proper name, and I'll go into that in a minute. But oil shale is another matter. Well, of course, that was a kind of gentler time, and we now know that bankers don't really care what the hell you call it, as long as you promise them that $10 million bonus next year. So let's talk about shale for a minute. First of all, oil. I mean, the English language is noted for its flexibility, its connotative richness. So whether you use the word oil to modify something and you mean that it actually has a liquid hydrocarbon in it, or whether you use it to say that this rock, if I cook it properly, produces a lovely oil, it doesn't matter in the English language. It's only engineers who are constantly insistent that there can be only one definition for a word or phrase. There's just, you know, there's no stopping them. The only other people who are really interested in nailing down the definition are politicians who have the Humpty Dumpty school of thought on this. The words mean exactly what I say them and nothing more. It's an important part of trying to seize the agenda by controlling the language. We had some absolutely marvelous examples of that earlier today. I mean, there was an entire talk that consisted of nothing but that. But let's take a look at what shale means. Now, here is Potter, Maynard, and Demetrius, the leaders in, you know, they wrote the book. That's the textbook on mud and mudstones. And they're saying that we use the word mudstone for all of these rocks, all these fine-grained rocks, whether they got this in them or that in them. And that shale, we go back to the definition from 1747 by Hewson, and it's a laminated, argillaceous, that means it's got clay in it, rock. Half the oil shales I've seen, even here in this state, would classify as shales by that definition. So, you know, it's really just an attempt to capture the agenda. It has nothing to do with science. It has nothing to do with what you're going to produce from it. The only thing I can say about it is that, you know, they want to use the term marlstone, which comes from marl, a wonderful four-letter Anglo-Saxon word. And here you see the definition, an old term, loosely applied to a variety of materials. It says, as the term covers a wide range of materials and designates no particularly well-defined composition, it should not be used without specific definition. So if you hear this old canard, you can say, why the hell are they talking about this? In fact, if you look at what these shales look like, this is a group of oil shales from another country, because this is the only place I could find quantitative data. Half of them would be argillaceous mudstones. They'd be perfectly good shales in that old definition. And half of them are marlstones, and then some are silty marlstones, and there's even a few silty argillaceous mudstones. It doesn't really matter what you want to call it. Oil shale is a very good and a well-used, comfortable field term. Field geologists use it all the time. I don't hear a lot of people, like in 40 years in geology, it's only a few people in oil shale that even use the word marlstone. That's the kind of thing that goes on in this field, is a whole lot of embroidery on simple, trivial points. So, CO2 emissions from oil shale, this is work that Adam Grant and I and Alan Burnham, who you heard speak earlier, have done addressing what we think the impacts would be of production of CO2 emissions from oil shale. There are two different major outputs: the direct emissions, that's the stuff you do in getting oil out of oil shale, and the indirect emissions, that's the CO2 emitted when you manufacture the steel, when you put all the vehicles together that you're using, etc. And because Adam has worked in this arena across all sorts of energy types, he describes it in terms of megajoules per ton of raw shale. I'll try to get this back to some larger scale issues of branded outputs of CO2 at the end. So there are emissions from retorting the raw shale. How much energy do you expend just heating the rock up? What other uses do you do around the site in getting the oil out of the oil shale? And how much CO2 comes out of the carbonate minerals that are an essential constituent of the rock, and the kerogen itself, because it has about 5% oxygen in it. And as it goes through this thermal cracking process, some of that oxygen will combine with carbon in the rock and form CO2. So, the thermal demand is dictated by a whole lot of features of the rock. They're listed here, and I think these handouts are going to be posted. Is that right?
Yeah.
Great, because we're going to run out of time really fast if we don't. And the range is this 450 to 750 megajoules per ton. If you can recover some of the heat, when you heat a block in situ, for example, if you can recover some of that heat, you can make this a little bit less. And Shell has plans to do that. They have two different things they'd like to do with that heat. One is to steam clean the rocks that they've extracted oil from. And the other is simply to transfer that heat to the next block to begin to preheat it. So how can you reduce that heat? You can reduce the shale quality, well then you don't get as much oil. You can reduce the moisture level. As was pointed out earlier, you want to pump out as much oil or much water as you can out of this block so you don't have to spend all of your energy boiling water. Slow the rate of retorting. These reactions occur at lower temperatures and thus require less heating if you give them longer to cook. That's the fundamental basis of Shell's approach of in situ conversion, is that the reactions take place 50 to 150 to 200 degrees lower in temperature. So there's less energy spent on heating the rock. In addition, they love the product they get. It's clear. That's what kept management going in oil shale at Shell from the fading off after Black Sunday through the next decade of oil production from Unocal, and then even on through the next 8 or 10 years until they became, in essence, the leaders in this area, was that they'd seen really good high-gravity oil that would require far less upgrading as a product. And then also you can reduce how much you decompose some of these carbonates. It's a pretty interesting problem. I may have to skip over the slides that show that, but here's roughly just the heating part for different types of heating. If you just burn natural gas in a downhole burner, it's 50 or so. If you use the same natural gas to generate electricity, it's 111 grams of CO2 equivalent per megajoule. And the coal values are higher. The average electricity balance in Colorado is a little bit lower. There's a really important point to be made here. A lot of the numbers you saw today, not only for CO2 but for water, were based on the use of coal. No company that I have heard speak about oil shale production has said that they intend to use coal. So that is a high number. That's a very high limit for both of these quantities, CO2 and water use. They will probably start using power off the grid, so you will have something like the mix for a period of time. But we will not get to large-scale production, as far as I can see, without moving towards that self-sustaining use of the natural gas that is a natural product of oil shale production. When I forgot to do my show and tell here, thanks to Glenn, I have a piece of oil shale. Fairly rich oil shale from the mahogany zone up there. And the oil derived from a similar sized piece of oil shale. So that's what you're talking about getting out of there. You do expend some energy getting it. There's no doubt about it. And it generally is more than you would need for most liquid forms of oil. But I'll tell you what, the oil you get out of this looks to me like much nicer stuff than the oil you dig out of oil sands in Canada. It's premature as opposed to overmature. It's not full of the degradation products of a lot of bugs chewing up the oil, which is what oil sand is all about. The auxiliary requirements, of course, depend on the method you're using. For in situ, it's the freeze wall, it's the subsurface cleanup, it's this reclamation phase, which is the dominant water user in a shell-type process. Far and away, the largest use of water, at least with current estimates, goes into environmental protection. It's the steam cleaning you do after you've finished pumping oil out of the rock. In addition, of course, if you're processing some of those surface-produced fluids, you're going to lose some of the water. There's going to be water losses. You're going to recycle your volume as many times as you can. And in fact, there's a really excellent opportunity for the federal government to support legitimate research on better water treatment facilities, because this isn't the only place in the country where we have water that might have some hydrocarbons in it. Really great opportunity for the federal government to really show that it is doing more than just verbal encouragement. Ex situ, that is mining and retorting. Crushing and pretreating uses water, utilities for any of the retort operation if you're using that, although many of these processes, again, are trying to live off either the remaining carbon that's left after you've extracted the oil from the oil shale or off the natural gas product. And then, of course, surface processing and produce fluids. The work that's got to be done before you put it in a pipeline, because at least for Colorado oil shale and for a number of other oil shales around the world, because this is immature stuff, it tends to be waxy. So you don't want to put it in a pipeline and end up with a system failure that leads to a very large candle. Let's take a quick look. Although it's a tiny fraction of the CO2 release, there are a number of reactions that can go on depending on what temperature you do your retorting at that produce CO2. Break down to some of these minerals of the calcite, that is phenomenal, calcite and dolomite, that are major constituents of the rock, and in some zones of nacolite, this exotic sodium bicarbonate. You notice that the name nacolite comes from the chemical formula NaHCO3. It is not nacholite, as I've seen it spelled many times. You get a certain amount for every weight percent in the rock that you burn up. You get a certain number of kilograms per ton. There's a whole set of classes that these then lead to. There are a number of uncertainties in these, and various models, including models that Alan worked on or was involved in at Livermore, show we don't really know for some temperatures. We don't really know very well how much of this reaction goes on, how fast it goes. So there's some uncertainties in there, but it's still a pretty small fraction of how much CO2 comes out in the end. But the other interesting thing, as far as I can tell, has not been examined in any of the literature, is there's a whole class of reactions that are actually going on in some of these rocks, and I've documented this now. It isn't yet published in some oil shales from Thailand, where there are reactions that are going on that probably occur at lower temperatures than the ones that were in that table before, and involve the constituent minerals of the rock itself and exchange water and CO2 in various different ways. They probably occur at lower temperatures than those other reactions, and may be responsible for whatever CO2 you see coming out of the pulp, out of the pipe in a shell-type process. We haven't really had a chance to discuss those with Shale or anybody yet. In addition, as I said, you oxidize the keratin a little bit as you're going on, so there's a certain part of the oxygen ends up coming out as CO2. This is, again, data that Alan generated, or Alan's team at Livermore generated years ago. And you get about 4 to 5% of the mass of the keratin as CO2. Finally, you've got some CO2 that's going to be produced from upgrading it prior to transportation. As I said, you've got to do a little work to make sure you don't turn your pipeline into a candlestick. And then after upgrading, refining will use some water. And these are numbers, again, from Alan's paper and the citations. I don't have the references here, but I can get them. So that may well vary on the quality, with respect to the quality of the oil shale and how far you upgrade it before you send it down the pipeline, and in the refinery, how far did you upgrade it before it got there. There's a probable net of, say, about 20 grams of CO2 per megajoule of refined product. Typically, the largest fraction of CO2 emissions from the production of shale oil comes from burning the fuel. This is even more true for virtually every other kind of hydrocarbon you can produce. But it's an extremely important point, because your ability to save, to reduce those emissions, is balanced between the part that the consumer has to do by driving a more fuel-efficient car, or by all those sorts of keeping it tuned up and things like that, and the part you can do, a producer can do at the front end, on the order of 70 grams. So what does that all look like not for the in situ retorts that I spent most time looking at, but for an above ground retort process, the Alberta Tessier process, that was originally planned to be used for oil sands, was adapted for environmental remediation, and is now being used. There's a very large unit that's been installed at Fushan in China and several other places. Again, you can see the top blue bar, the top part of the bar, the blue is the combustion of the fuel itself, and these other inputs are the ones, and Adam has a low and a high range that he's calculated there. And you can see the comparison to conventional oil. It is warm. It's substantially warm. Somewhere between, I think in our final calculations, we estimated 25, perhaps 40 or 45% more CO2 emissions from making and burning oil shale. Here's a comparison for a wide range of technologies. And then on the last one, there's an error bar that relates to mainly the production side. That's a set of calculations I did using trying to capture our uncertainties in how much CO2 emissions you get. And that is shown here. This is a fairly simple model, and yet it is capable of incorporating a very large number of parameters in a very visual manner. It allows me to sit down with anybody and show them exactly how I got the answer I got. And if they've got a better idea about either what the distribution of values that ought to go into this model ought to be, or how the variables ought to be related to one another, I can make changes in that. In the course of a day, sitting down with 3 representatives from my sponsors at CoStar, I changed the water consumption figures I had by more than half an order of magnitude, by a factor of 5 or 6. Just by changing things on the fly, sitting there with these answers. This tool then is a great way to manage the interaction with people to say, here's the numbers and here's how we got there. What do you think is wrong if you don't like the answer that came out, and how can we improve the model? It allows me to talk to anyone, and as long as, so far there's nothing in here but algebra. I think it has a great opportunity to look at uncertainties and to support better decisions. So here's the results I got. The most important factor in here is how efficiently do they get the oil that they can get out of the rock. That's what's known as, this is the percentage of the Fisher assay, which is our traditional measure of how much oil is in that rock. It's the most important. What's the efficiency of your power plant? How much kerogen is in the rock? And then you get down to smaller and smaller importance of these other variables. So to look at, in terms of the actual output in million tons of CO2 per year from a 3 million barrel a day oil industry producing oil shale, because that's where I started from. You can see that there's some pretty high values in there, but they're fairly sparse, and they're drawn from the far fringes of the probability matrix that we've got here. And it's very strongly dependent, of course, on this production efficiency. For comparison, I believe 300 is about the emissions of Saudi Arabia. I think 150 to 200, somewhere in is the emissions of Thailand or some other country like that. So this would be a major industry. It would be a major output of CO2. There's no doubt it would be a large industry, just as the oil industry is right now.
Is this life cycle, or is this just...
This is mainly getting it out of the ground, because that's where I started from.
So this isn't...
So I did not add the upgrading part. I had not had the chance to interact with Adam and get the upgrading part, but that's what he was trying to show in that error bar added onto one of his graphs. What can we do to mitigate this? Well, we could use a low CO2 heat source. Jack Ridges has suggested off-peak wind power. Install a lot of wind power. We're certainly growing our wind power resource. How sustainable that growth is, I'm not sure. We've tripled our wind power production capacity in the last 4 years, I think it is, something like that, as a nation. Can we go on doing it, growing at that rate? It's an interesting question. It's been suggested that we use nuclear. I've heard a lot of entertaining off-the-wall ideas from Charles Forsberg. Somebody needs to follow behind him and decide which ones are really working, which ones are totally off the wall. Nuclear power is a possibility, but he has in mind injecting molten salt into these wells down to do the heating, and I think that's completely off the wall, based on my work at Los Alamos and before. You can reduce the losses in the heat transfer to the shale, use the heat directly rather than creating electricity and putting it underground. I mean, when you generate electricity, this seems to be lost on a lot of Americans, it's got to be generated by some means. Right now, a huge fraction of that is done by burning hydrocarbons. And it's not absolutely clear how quickly we'll be able to change that. And of course, you can increase the scale of molecular heating to reduce the heat loss. But I'm seeing a sort of slow, steady convergence in that area, simply because people are recognizing they also need to maintain the structural integrity of the 1,000 feet of rock they're heating and extracting 20% of the volume out of it. So that is a further limit on how big you can grow the heated block you've got. Did I get through all those? Of course, you can capture the CO2 and store it. This, to me, is the future of energy use in this nation. It's a huge challenge. It requires building an industry the same scale as our petroleum industry. It's 1 carbon atom for 1 carbon atom. That's what we're doing here. I forgot, reduce temperature so that you eliminate that carbonate decomposition. That may not be entirely done if you've got some of these lower temperature reactions going on. But again, the slower the rate of heating, The better the product and the less heat you have to put in, but the slower you get your goodies. And as I say, CO2 capture, I think, is going to be extremely important. So the main sources of additional emissions are the heat of retorting and the carbonate decomposition. Minor sources, mining and pre-processing or refining and upgrading in some cases. And then mitigating them is reduce the temperature, reduce the intensity, increase the fraction of the primary heat that gets into the rock. I'd like to put it in a broader frame of environmental issues. An environmental workshop we held in conjunction with the symposium identified water quantity and quality as central issues at least 4 years ago. This is nothing new, and a lot of work has been done, put in on it. The uncertainties are nowhere near as large as they are often portrayed. And the people who are portraying them that way usually have not been in any of these meetings. Air quality, I think, is important, but I think it's going to be less important. Surface and ecosystem impact. One of the interesting things about oil shale is because the resource is so concentrated aerially, it is likely that the footprint will be quite small. For example, if you were operating on about 10 square miles at a time, and it took you 10 years to get through the full production cycle, you would be exhausting about 1 square mile every year. That would be about 3 million barrels a day. So instead of having a network of roads and pipelines and dozer pathways across the Piceance Basin as already existed for the gas development, you'd have very concentrated development within that 1,200 square mile area that would move steadily across the land and would be fully reclaimed before you really moved on to a huge new area. That has been very little talked about. There is a huge amount of impact assessment and policy assessment, development of new models to try and understand these impacts, all of these data needs and modeling needs, etc., which legitimately are federal roles because the federal government has stewardship of these lands and is the only entity I know that has that responsibility. No one leaseholder has that responsibility. So whether it's by coordination, as was done in the 70s and 80s, with a group that many people participated in, or whether it's some kind of new tax, or whatever they want to do, the companies feel, well, I already pay a lot of taxes. Why are you not doing this already? I guess I would have to say in the government's defense, it's just never really wise to bet on the government moving too fast. You know, that's the way it is. I've been a federal bureaucrat for 5 years. I've beat my head against the wall trying to move things forward. It just doesn't happen that fast. What about another issue? We talked about water, and to me, water is truly the big issue here, but it's the big issue for all kinds of alternative fuels. If it's a problem that an oil shale industry might use as much water as Denver does, what about a biofuels industry that might use 10, 50, 100 times as much water? And even if you move east, I'm sorry, the national water situation is not so great. We've got lots of aquifers getting contaminated with phosphates, with nitrates, with, in the case of up in Ontario, road salt. People's wells are turning up salty because of the roads that are quite some distance away in some cases. The entire aquifer, and the suggestion was it would take 100 years to remediate that. So actual water use, whether it's here in the rural, in the arid West, or in any other part of this country, is a critical issue. Now I know that biofuel producers are working on this issue, but so are oil shale producers. Part of the political discourse is to refer to these as dirty energy, or to refer to the alternative energies as 21st century energy. Well, wind power we know is not 21st century energy, or else those Dutch masters were painting something entirely out of their imagination. Wind energy is a technology that's been around for a long time and keeps getting technology improvements. Coal used to be a hell of a lot dirtier than it is now. So is it wrong to think we might be able to use coal in a clean way, now that we've discovered a new measure for clean CO2 content? You know, solar power has been used for millennia. Now, it was not in the fancy, they hadn't invented photovoltaics, so that one we could consider a new energy source. But it's been around for 50 years. It's so wonderful. Why doesn't every roof have one on it, you know? We don't have a solar cell on every rooftop, and it's been around for 50 years. Then, gee, it must not be a good idea. I don't think so. I don't feel that way. My feeling is that we have a very big challenge in the next couple of generations. We have to make a substantial energy transition. I believe in that. And I also believe in an old Arab proverb that says, if you think you'll solve the problem in your lifetime, you haven't taken on a big enough problem. I think that's what we've got here. We don't have that issue with this one. We've got a big problem, and we're going to have to make a transition, but it isn't necessarily going to happen overnight. I've done a water model of the same kind that I did for the other. It's not yet complete. I've presented preliminary results. The same thing holds. You can go in there and anyone can look at it and tell me what I did wrong in the logic. And once you get the answers out, some obvious conclusions come forward, and some decisions look stupider than others. How fast is this going to happen? They did a talk called 1 million barrels a day. When and how? This is projections of shale oil production from various countries that are in the process of doing oil shale or looking towards doing oil shale. When you integrate it, it looks like the blue line. Those projections go up like this. That's a growth rate of about 14% per year, starting, say in 1999. That compares to my numbers for oil sands, just about 10% a year, going back to the late 1960s. And for the U.S. oil production from 1862 to 1919, going up at about 9% per year. So when you take on the business of building a new energy source, it doesn't happen overnight, and sustained growth is more likely to be in the range of these 8, 9, possibly 12%. We heard that number before. It's going to be a real challenge for any new energy option to reach that kind of level. Shell has made projections of what it thinks the energy future is going to look like, and they have two scenarios: scramble, where everybody tries to do whatever they can and there's no coordinated effort, and you end up with a very large fraction of your energy coming from oil, gas, coal, and nuclear. And of course, a huge amount of that new energy is out there in Asia, in the developing countries of Asia and Oceania. In a more coordinated scenario, you begin to see much more of a turnover. The hydrocarbons are beginning to decline as you get out to 2050. It's an important change, but it's still a huge fraction of the energy resource you're using. Renewables are on their way. I believe that. A lot of them. But they all have the same kinds of challenges that oil shale does. So I would say globally significant production is still decades away. 25 years. It's going to take a long time, barring some major technological breakthrough. And even if that happens, technology may not be the rate-limiting step. If everything has to proceed at a very slow level in order to reach consensus on it, which it may have to do, it's going to take quite a while. But the same is true for virtually all alternative fuels. And stable growth can provide the time to enable carbon management. We've got a lot of time here before these issues become huge and unmanageable. And in fact, had we imposed the same demand to prove economic viability and to prove every aspect of the management of oil production, we would have finished off killing the whales. And then we'd have been looking for another resource. What we do in the way of technology now in the oil and gas business bears virtually no resemblance to what Colonel Drake did in Pennsylvania in 1859. And I have to say, my research at this point, actually, most of the stuff on CO2 and on water has nothing to do with this. I do it in my spare time. I'd love to have funding for it, but I haven't gotten any bites on that. The membership that I support is Total, Shell, ExxonMobil. These are not their opinions, nor am I in any position to speak for those companies, because the president of Colorado School of Mines will boot me if I even appear to be speaking on behalf of those companies. My research team includes folks at the School of Mines, the University of Wisconsin, at Binghamton University, and ultimately we've had conversations, we haven't yet gotten to the stage, where the National Center for Atmospheric Research will do paleoclimate models in the Eocene when those rocks up there in the Green River were deposited. They're excited, we're excited about that whole exercise. And finally, I come back to the Oil Shale Symposium, and I say again, 300 people from around the world addressing all the problems we've talked about today. Christy Hamrick from the Rifle School, from one of the Garfield County school districts, talking about the kind of nightmare scenarios they've seen. And people talking about the water issue, talking about all the environmental issues. It's a very exciting time, a really good field trip as well. If you actually want to know what's going on in Oil Shale, you have to be there. Thanks.
Thanks, Jerry. And we're going to take a short break. We'll try to keep it real short. We're going to come back to one last panel and just really try to have a discussion with the whole group about where we go from here on oil shale issues. So I hope you'll join us for this last session.